You're listening to Wurth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're checking in with leading industry experts and Wurth Electronic technical specialists who will shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. When we talk about power supplies, very rarely are transient conditions thought of immediately. Because power supplies are often designed for steady state operation, these transient conditions are mainly considered as an afterthought. So in practice, transient conditions such as startup, shutdown, and load transients are often far more stressful on the components of the power supply than operation in steady state. In order to suppress high-frequency noise, chip bead ferrites are mainly placed at the input and the output of power supplies. There are two good examples of transients that are often overlooked but requires very careful attention. First, the inrush current. This occurs when a power supply first starts up or when PWM used for variable loads such as dimming of LED drivers. Chip bead ferrites are often positioned at the inputs and the outputs of power supplies where they must endure heavy transient currents, and this creates a need for compact, cost-effective devices that are also highly reliable. Such ferrites are placed at the input and the output because they are very effective at filtering the high-frequency noise in switching regulators. This high-frequency noise results from rapid switching currents ringing with parasitic inductance and capacitance. Such noise tends to occur at frequencies between 50 up to 500 megahertz and is known as ringing, spikes, or periodic and random deviation noise, also known as PARD noise. In our example, when we measure the PARD noise at the input and the output of the switcher, we can measure the noise to be at a frequency of 170 megahertz. Conducted noise like these waveforms will generally radiate noise if it leaks into the input and output wiring harnesses. Generally speaking, chip bead ferrites should always be placed as close as possible to the converter as source of noise. However, one effective method for preventing PARD noise from getting into the input and output leads of a switching power supply is to place the chip bead ferrites in series with the inputs and the outputs. As shown in our attached figure 1, these should be placed as close as possible to the edge of the PCB and or to the connectors, and footprints for ferrites should be placed in series with both the positive and negative of each connector. Again, in general, ferrites should be placed as close as possible to the source of the noise because the noise couples into the unfiltered traces and cables. However, we need to be aware that it is very likely that high-frequency noise can couple around the ferrite through parasitic capacitance to GND and earth planes. Most EMC standards begin limiting radiated EMI at 30 megahertz, so preventing this unwanted antenna effect of input and output leads is very important. When a ground plane or shielded enclosure is present, noise can couple around a ferrite placed towards the interior of a PCB. In this example, the PARD noise gets around chip bead ferrite beads by coupling capacitive through the ground plane and earth to the input and output of the connectors. Wurth Electronic has developed a family of chip bead ferrites that features high average and RMS current ratings, low DC resistance, and are also tested and specified for high current pulses. This peak current proof series, the MPSB Multilayer Power Suppression bead family, is especially suitable in positions where short duration currents far exceed the average currents. Next, we'll discuss the inrush currents at turn on. Now, at the moment, when a power supply is turned on, any capacitors connected to the input bus will begin to charge. In some very rare cases, a soft start of the input supply controls the ramp in a smooth, monotonic behavior, but in most cases, the input voltage ramps up very quickly. For example, if a 12 VDC power bus is already up and running when a mechanical switch connects it to the buck converter, The ramp slope is only limited by the source resistance and the resistance and parasitic inductance of the leads, the PCB traces, and the switch. For our example, the resistance and the inductance of a 30 centimeter banana-to-banana test cable was measured, and it came out to 8 milliohms and 0.3 microhenry respectively. In practice, all voltage sources are current limited, but if the 12 VDC bus had a large amount of output capacitance, then the charging current when the mechanical switch closed could easily exceed 30 amps. In our attached figure 2, it shows a pulse that peaks at approximately 33 amps, and then it settles after around 100 microseconds to the 5 amp current limit of the laboratory power supply used as the input source. It then takes another 200 microseconds to charge the input capacitors up to the target 12 volts. We can compare this waveform to the steady-state input source current, and this formula can be seen as attached figure 3 in this podcast. Now, in this case, the compromise facing the circuit designer is really quite clear. Any input filter components must be able to handle heavy current pulses each time the converter is switched on. But selecting ferrites rated to handle the full pulse current leads to over-design for steady state. Next, we'll take a look at the same test buck converter, but focusing on the output. Now, the converter has two polymer aluminum 330 microfarad output capacitors with 20 milliohms of ESR each and two 100 microfarad multilayer ceramic capacitors with approximately 3 milliohms of ESR each. This capacitor bank is capable of supplying large pulses of current in a short time. The same 30 centimeter cables were used to connect the 5-volt output to a load that draws the max of 8 amps of output current, and our tests show that when the 8 amps load is connected with a fast rise time, the current transient comes close to around 25 amps. So what problems did we face with steady-state current ratings? Well, the MPSB family was actually designed to provide a similar range of impedances as the standard family of chip bead ferrites. The CBF standard family provides RMS current ratings, but like nearly all other chip bead ferrites from any manufacturer, no peak or pulse current ratings. So in this example, in order to handle a 33 amp pulse with steady state specifications, we would need to multiply the CBF family devices, since the highest RMS current rating in this family is 6 amps for the 1806 or the 1812 size components. Just one CBF family device would handle the steady state current, but repeated startup transients could lead to failures. In this instance, we would need 6 such devices for the positive input line and then another 6 for the negative input line. And this just isn't practical for several reasons. First, chip bead ferrites can be paralleled for continuous currents, and their positive temperature coefficient will ensure that they share current more or less evenly. However, such current sharing is neither tested nor guaranteed for short duration pulse currents. Second, placing several components in parallel with impedance that is dominated by resistance and inductance causes the inductance, the resistance, and the impedance to drop, making them far less effective at filtering the desired noise. And third, 6 components means higher cost and much needed PCB space. In situations where peak currents exceed average current ratios from 3:1 to nearly 10:1, the MPSBs are typically used. A first pass for selecting chip bead ferrites is to review all parts that can handle the RMS current of 3.7 amps. In our example, we're expecting around 10,000 switching cycles during lifetime, so 10,000 pulses with 33 amps will definitely stress the MPSB of the input filter. The first step, and definitely the most comfortable way to do this, is to enter the data into the Pulse Designer of RedXpert. From RedXpert, we can see that there are 9 parts left, which we then took into product storage for easy comparison. Now, from the remaining 9 MPSB left, we can select the one with the highest resistance, not the total impedance, at the noise frequency. In general, chip bead ferrites have their highest resistance at the frequency of their highest total impedance. But for other frequencies, there's no general approximation possible. The fastest way to find the best part is to use the Red Expert platform from Wurth Electronic. You can find that online at www.we-online.com/redexpert, or even click the link available in this podcast. As a registered user, you can place the chart slider at 170 megahertz and then directly read the resistance values of each part out of the grid. You can even sort them by descending to get the part with the highest resistance. After considering all of our parameters, our red highlighted part seems to be the best suitable component for our application. Its current rating is 4.0 amps, and it can withstand around 18,700 pulses of 33 amps and 8 milliseconds length. Keeping in mind that this 8 milliseconds is much longer than the initial pulse of 500 microseconds, and the short peak of 100 microseconds gives it plenty safety margin. From all suitable components, it is the one with the highest resistance at 170 megahertz. The output RMS current is the same as the average output current of 8.0 amps. Following the same guidelines, we see 5 candidates rated for greater than 8.0 amps. All 5 of these parts can handle more than 10,000 pulses and have more than 8 amps RMS current rating, so the final selection will require actual EMC testing to determine which part filters the most noise. The smaller parts are less expensive, but provide less reduction of noise. For final lab testing, we added our previously mentioned WE MPSB component to the input and another to the output. In our attached figure 4, we can clearly see that the green output voltage is now silent compared to the unfiltered voltages. Performing radiated EMI scans proves that the chip beads successfully suppress the PARD noise, especially in the range of 170 megahertz PARD ringing. The EMI is significantly improved. Further considerations include the influence of DC resistance to overall efficiency. The MPSB component we used has a DC resistance of 35 milliohms, which adds additional conduction losses and therewith reduces the efficiency. The measurements in our lab showed just a slight decrease of the efficiency from 95% down to 94.5% for each used chip bead ferrite. As with all magnetic parts, chip bead ferrites also allow the physics principle of elementary magnets. With increasing DC current, they will continuously saturate up to the level of complete saturation. This saturation effect shifts the impedance curve. The peak inductance value remains almost constant with a drop of just 40% of its initial value, whereas the impedance at lower frequency significantly drops by rates of up to 90%. In low frequencies, the inductive part is dominating, which saturates with DC current. In our example before, the SRF, the capacitive part, is dominating, which is not affected by the DC current. However, if you do your EMI measurements at full load current, this worst case impedance shift is already considered in your measurements, and you don't have to care about this effect. It's important to note that the bigger the size of the chip bead ferrites, the lower the shift of impedance caused by the DC current. In conclusion, chip bead ferrites are the best components for reducing high-frequency noise above 10 megahertz. In power supply layouts, they must be placed as close as possible to the source of noise, which can be the input and output connectors, to properly filter conducted EMI from the input and output wiring harnesses. This prevents conducted EMI from becoming radiated EMI. Being the first components and also the last components in the chain exposes chip bead ferrites to heavy transient currents, and circuit designers can now select parts that filter noise with minimal impact to power efficiency and will handle large current pulses with excellent reliability. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Wurth Electronic online at we-online.com/appnotes. You're listening to Wurth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who will shine a light on our topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast.